In this supplementary video, I will solve problem 14 and problem 30 in exercise 4. So these 4 problems have a lot in common with what we have done in class. So that's why I decided to solve these 2 problems first. The rest of the problems will be done in a separate video. So for problem 14, you are asked to evaluate the limit, namely the limit of the root of this fraction at infinity. So, and you need to provide justification for each step by indicating the appropriate properties of the limits. Okay, so we will just use our standard technique to divide this fraction both on top and on the bottom by the highest power of x in the denominator. Well, in this case, the highest power is precisely x cubed. So, but because we are asked to provide the justification for each step, so let me just write it out very carefully. Since I'm interested in the limit as x gets very large, so in particular, my x over here is not going to be take 0. So since x is non-zero, so I will rewrite my function in question, 9x cubed plus 8x minus 4 divided by 3 minus 5x plus x cubed. I will be able to rewrite this guy as follows. So I will just divide both on top and at the bottom by x cubed. So after the division, my numerator becomes 9 plus 8 divided by x squared and minus 4 divided by x cubed. And my denominator now becomes 3 divided by x cubed plus minus 5 divided by x squared, and finally plus 1. All right, so because x is non-zero, so I can perform such operations to rewrite the whole thing in this way. So if we are not asked to give the justification, you can simply evaluate all these guys to be 0 and to get the conclusion to be root of 9, which is going to be 3. But now we need to provide justifications, so I will prefer to write it in this way. So as x approaches positive infinity, we know that 1 over x approaches 0. Then by the power law, we see that 1 over x squared approaches 0 and 1 over x cubed approaches 0. So to conclude all these guys approaches 0, I also need to use the constant multiple law. So let me write it down. By the constant multiple law, we conclude that 8 divided by x squared approaches 0, minus 4 divided by x squared, x cubed approaches 0, and 3 divided by x cubed approaches 0, and finally minus 5 over x squared approaches 0. So we conclude that all these guys approaches 0. Then by limit of constants, so we see that the constant 9 has the limit 9 and the constant 1 has the limit 1. So we can now use the sum law to conclude that the numerator inside the square root. So 9 plus 8 divided by x squared minus 4 divided by x cubed. So this guy is approaching 9 plus 0 plus 0, and the answer will be 9. And moreover, the denominator, 3 over x cubed minus 5 over x squared plus 1, this will have the limit 0 minus plus 0 plus 1, and the answer will be 1. All right, so that way we know the limit of the numerator and the denominator. In particular, because this denominator does not approach 0, so we are allowed to use the quotient law to conclude that the fraction 9 plus 8 over x squared minus 4 over x cubed divided by 3 over x cubed minus 5 over x squared and plus 1. So this guy approaches 9 divided by 1, and the answer will be 9. So this is what you could obtain by the quotient law over here. And finally, you can apply the power law. again. So where now the power is taken to be 1/2 power, so namely the square root. So we can conclude that root of 9 plus 8 over x squared minus 4 divided by x cubed over 3 over x cubed minus 5 over x squared and plus 1. We can conclude that this guy approaches root of 9, and the answer will be 3. Finally, because this equality holds when x is large, so we simply conclude that the limit of what we are interested in, so root of this fraction, so this is going to be equal to 3. All right, so this will be the full justification of this limit computation over here. For number 30, there are multiple ways of handling this problem. And let me just use the algebraic method, then I will just use the comparison. So first, because as x approaches positive infinity, so we know that x squared is also going to be very large, and x squared plus 1 being 1 plus a very large number, this is also going to be very large. And now you need to use the fact that if y approaches infinity, then root of y is also approaches infinity. So this is something like the power law for infinite limits over here. Okay, so so using this fact, then we can conclude that root of x squared plus 1 is also approaching infinity. So in other words, we've managed to show that limit of root of x squared plus 1 as x approaches positive infinity. So this is going to be positive infinity. All right, so this is just one simple way of using algebraic limit. Okay, alternatively, you can also use the following argument. Note that when x is positive, so x itself is the same as its absolute value. We have seen earlier in class the absolute value of x is precisely root of x squared, but root of x squared is going to be strictly less than root of x squared plus 1. Okay, so we know that root of x plus 1 is going to be strictly larger than x. Okay, so if x approaches positive infinity, this means x gets large. So then from the inequality above, we know that root of x squared plus 1 is even larger than x. So from this argument, you'll be able to see that root of x squared plus 1 is also approaching infinity. So in other words, we managed to argue that the limit of root of x squared plus 1 equals to positive infinity as x approaches positive infinity. All right, so that will conclude this supplementary video.